Good evening, everyone, and welcome to our second weekly discussion session for the Physics of Nanoscale Devices NPTEL course. Now, before we begin with this session, due to some network issues on my end, I'm unable to host the live meeting that this discussion session is supposed to be a part of. We are having an institute-wide network problem over here in IIT Roorkee. So because of that, I've kept the meeting open. So as and when any people join, they may listen to this session live. Nonetheless, I shall be going through the material that I'm intending to cover for this week, and the recorded version of this will be uploaded on the YouTube playlist, and the slides will be available on the corresponding Google Drive. So with that, let me begin today's session. So as I mentioned before, this is our second weekly discussion session for the Physics of Nanoscale Devices NPTEL course, and I am Jyotishwaran, a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So the topics that we shall be covering in today's session are as follows. So we shall be looking at the Kronig-Penney model. So these topics correspond to the lectures in week 2 of the NPTEL course. And so the topics that shall be covered in order are the Kronig-Penney model, the electronic band structure in solids, the notion of effective mass, and we shall end the discussion with the idea of the 3D density of states. So these are the 4 topics that we shall be looking at. Of course, everything that is being discussed here will also derive from the discussions that were conducted last week. So first, let us begin with the Kronig-Penney model. The Kronig-Penney model is a toy model that represents a one-dimensional solid in that we have, let me just pick a right color here. So what we mean by that is we have an one-dimensional array of nuclei, and so this thing goes on in either direction, and the period of this 1D lattice can be some capital L. So the potential energy an electron will face in this lattice, V of x, this is a one-dimensional lattice, so this is the direction, positive x direction. So V of x, we can say that will be equal to V of x plus L. So this is a periodic potential energy. Now here, of course, the Kronig-Penney model, the reason I'm calling it a toy model is because we are not representing these potentials by any realistic potential energy function. We are instead representing these environment by what is called a square well potential. So what is a square well potential? Like last week we discussed what is called the 1D box or the infinite potential well. Now a square well is a potential well with a finite depth. What that means is it is a potential of this form where, sorry, let me just redo it. So it is a potential of this form where we have, say, a region from here to here, and let me call this energy some V0, and this can be a non-zero value, but since energy level scaling is relative, I will set the lower value here as 0. So this is 0 on the energy scale. So a square well potential is essentially a function that is V0 everywhere else in space and 0 in a region from some point x1 to x2. What we have here is a periodic version of this, which means this structure shall be repeating itself periodically. Therefore, the Kronig-Penney potential So this is a single square well. So this is a single square well. Now the periodic analog of this will be, for those who are familiar with signals, it will essentially look like a pulse string. So there will be a region where the potential is V0, then there will be a region where the potential is 0, then there will be another region where the potential is V0, and so on. So the function will progress periodically in this manner. So for our purposes, I shall say that this region here is width A, and I'm going to call this width B, and I will say A plus B is equal to L. So this valley region essentially corresponds to the low energy domain. So that will correspond to the region surrounding the nucleus in our toy model. And the high potential regions are in the midpoints where the electrons are somewhat far away from the two neighboring nuclei. So this picture can be superimposed over here. I have a graph, like a proper image for this, which we shall use in one of the subsequent slides. This is just for the purposes of representation. And the aim of all of this is to understand the formation of band structures. So how do we arrive at the band structures? So we shall do that by solving a problem. So as mentioned before in the previous slide, we have this potential well. So I have defined it formally over here. So it is defined in the region 0 to A to some A plus B, which I'm calling L. So A and L. So what I'm saying is, in this region, the potential is high, like it's V0, and then in this region, the potential is 0. So this structure repeats itself periodically. So this is a periodic square well potential. Now our exercise in this problem will be the derivation of the boundary conditions. So let us see how we are doing that. To the one member who has joined this meeting shortly before, the reason for the delay and the haphazard mode in which this session is going is that we are having some local network issues. So previously when I set up the meeting, I was constantly dropping out of, like my internet connection was dropping out. So now I've made some alternate arrangements. Hopefully this connection will stay. Nonetheless, the recorded version of this video will be made available to everyone of this session. The video will be the recording. So I duplicated the slide. I didn't want to duplicate it. Let me insert a new slide. Yes, come over here and get rid of these things. Yeah. So now our problem has two regions. Essentially, okay, first, before even starting, the general solution for this problem, solution for a periodic potential, is given by the Bloch's theorem. So it is given by the Bloch's theorem, which states that the solution psi of x will take a form e to the power I kx times u sub k, like it's just a label here, uk of x, where uk of x is a function with the same periodicity as the lattice. Therefore, uk of x will be uk of x plus L. So how do we go about? So the aim of the entire like Kronig-Penney model solution is to identify this function uk of x and what values will be present in it. So how do we go about doing it? We do this by considering the two regions. So here, similar to how we solved the particle in the 1D box, we essentially solved the wave function in the region where the potential was infinite, and we solved the wave function, solved the Schrodinger's equation in the region where the potential was infinite, and deduced that the wave function will have zero value over there. And then we solved it within the well, obtained the different possible functions, and we matched the two using boundary conditions. So we shall do the same thing here. So the two regions that we have are, we have two regions. I don't know why I hyphenated it. Can I get rid of it? Yeah, good. So the two regions are as follows. So first is X belonging to 0 to A, and the second region is X belonging to A to A plus B. So I'm putting the open intervals on both of these sides just to indicate the discontinuity of the potential energy function. Otherwise, it's just a formal usage here. Now in this region, I know V of X is V naught. And in this region, I know V of X is 0. Now first and foremost, what kind of solutions are we looking for? That should be important, because in the case where I have an existing ambient potential energy, here we know there are two kinds of solutions. And what are the two kinds of solutions? They are the free particle solutions and the bound state solutions. So what are the free and the bound state solutions? Here E is greater than V naught, and here E is less than V naught. Both of these situations are physically realizable, but here we are concerned about, like, from a physical notion, we want to study the behavior of electrons in solids. So by that very definition, the electrons are bound to the solid. So we shall be concerned only with the bound state solutions. So we shall be looking at values where E is less than V naught. Now, I recommend people to go back and look at the solutions for the bound state case. So first, I am solving for X in 0 to A, where we have, how do we write this? Yes. So here the general solution psi of X, since we are talking about the bound state solution, will be represented as A e to the power beta x plus B e to the power minus beta x, where the quantity beta, now it will be a real number because E is less than V. So that is given by square root of 2m oh no, it should be V naught minus E because the quantity under the square root should be positive. So yeah, so V naught minus E divided by h bar square. The denominator, the whole expression is under the square root. Okay, so this is beta. And I could have also used alpha. I don't know why I suddenly leaped on beta, but nonetheless, we shall continue using beta. And in the second region, that is the case where V equal to 0. So in that, the particle effectively behaves as a free particle. So we know the solutions there to be, if we are following the previous session's conventions, it will be of the form A e to the power ikx, B e to the power minus ikx. But what I'm going to do is, the reason why I represented the functions like that is, had I written them as A cos kx plus B sin kx, then that would have amounted to an assignment solution. So for that purpose, I use the alternate notation. So now I'm just going to write the trigonometric form. The free particle solution can be written as some C cos kx plus D sin kx. So this is the wave function in the, like, the zero potential region. So here, of course, k is given by square root of 2m E by h cross squared. So essentially what we are doing is, if we know that the particle is a bound state with energy less than V naught, lying in this region, in this potential, then depending on which region it is, the wave function will be of these two forms. So now that this is known, what we have to do is we have to make sure that two conditions are satisfied, and the two conditions are psi of x must be continuous and psi of x, or rather d psi of x by dx, since this is a 1D problem, we don't have to take partial derivatives, is also continuous. So these are, yes, so these are the two conditions that needs to be obeyed. So that implies psi of x at 0 plus is equal to psi of x. So what we have to remember is, in this case, there are four boundaries. There are three boundaries. So there is the boundary around 0. So there will be a boundary from this side, a boundary from this side, a boundary from this side, and a boundary from this side, and a boundary from this side. What we will see is that, and yeah, in this region, so there will be like three boundary conditions, but we will see something interesting that is happening here. So 0 plus should be psi of x at 0 minus. Those 3 points were the discontinuity points in our potential representation. And secondly, we will have psi of x at a plus is equal to psi of x at a minus. And finally, we will have psi of x at L plus is equal to psi of x, psi of x at L minus. What that means is, so now we have these three conditions. But if we look at this situation here, let us just look at what the potential actually looks like. So over here, again, the potential will drop down and go like this. So since this is a periodic potential, here from 0 to minus a, my potential will again take 0 value. And after that, from minus a to minus l, it will again rise to the high value of V naught. So this is V naught, this is 0. So any condition that I'm applying over here is actually equally valid over here, because the environment here, 0 plus is the same as L minus. Sorry, 0 minus is the same as L plus, and 0 plus is the same as L minus. Yeah. So what do I mean by 0 plus? It means 0 plus delta, a small region to the right of 0, and 0 minus is a small region to the left of 0. So whatever is here is the same as what is present. So whatever is to the left of 0 is the same as, 0 minus is the same as L minus, and 0 plus is the same as L plus. This is due to the periodicity. Therefore, I need not take all the three boundaries. Only two boundaries are sufficient. And this is the reason why I put open intervals here. Because the only points that I need to consider for solving, getting the solutions, are 0 and a. A plus b is the same as 0 because the potential is periodic. However, this a plus b will play another role, which we will see pretty soon. So this last condition over here is no longer required. Let me just keep it and let me mark it and say this is redundant. I'm not going to erase it because that way any person who is just reading the slides will not understand why I'm doing some things. Redundant. So this is redundant, which is why we shall not be considering it. We shall only take these two cases. So what does that imply? Now psi of x at 0 means we will have to take the in 0 plus, like to the right, this function will be the exponential function. So this will be the exponential function, and so over here the wave function in this region will be my exponential function. To the left of 0 it will be a trigonometric function because of how we have defined our general solutions. So it is exponential here and it is trigonometric here. Similarly, to the right of a, the function is again going to be trigonometric because there v of x is 0, and to the left of a, I'll again come back to my exponential function. So in 0 plus, if I substitute x equal to 0, we will have a plus b. Oh, let me just change the color. Yeah, so in 0 plus, so this is the 0 plus 0 minus domain. So over here what we will get is, if we go back and look at the function here, it is the exponential. So if I substitute x equal to 0, the exponential terms will essentially vanish. Not vanish, they will become 1. So that will imply a plus b is equal to, it is a trigonometric function here, which is c cos kx plus d sin kx. Again, setting x to 0 will get rid of my sine term. Only the cos term will be there, and even that will be equal to 1. So the first boundary condition that we have for this equation in the form that I have presented is a plus b is equal to c. And the second boundary condition is, so we have 4 unknowns over here for a given energy. I need to find out a, b, c and d. So we need to get 4 equations. The second boundary condition is in the L plus L minus, sorry, A plus A minus region. Plus A minus region. So we know that in A plus we have the trigonometric function. So that implies C cos K plus D sin K should again be equal to A e to the power beta A small a plus B e to the power minus beta small a. So this is the second set of boundary conditions. Now from the derivatives should be continuous, what we will get are again 2 more adjoint conditions to this. So in that case what we have to do is we'll have to take the derivative of this. So we will have the beta coming down when we take the derivative with respect to x, and over here, and of course a minus sign will be introduced. Similarly here the cos function will become minus sin x and the sine function will become cos x. So I'm not doing the derivatives here because I mean it is reasonable to expect that all of you will know how to take derivatives of standard functions. So the trigonometric side, sorry, first over here when we are talking about the continuity of the derivatives, once again on the left hand side the exponential terms will become 1. So what we will be left is a beta minus b beta is equal to, on the left hand side I will have c minus sin k sin kx plus d cos kx. So now the factor corresponding to c will vanish. So what we will have here is dk. Yes, this implies a minus b into beta is equal to dk. And similarly over here, all I have to do is take the corresponding derivatives here for these functions. So that will be ck cos ka, oh sorry, not cos ka, it will be minus ck sin ka sin ka plus dk cos ka which is equal to a beta e to the power beta a minus b beta e to the power minus beta a. So this will give us the four equations that we need to solve for the values of a, b, c and d. But our problem actually does not end with this. What we need to ensure is that Bloch's theorem is also satisfied. So essentially after this, we will also have the condition which says psi of x equals psi of x, sorry, apologies, I should rather write it like this. I should say psi of x plus L is equal to e to the power I k L times uk of x, because uk of x plus L is uk of x. So this thing should also happen. So whatever psi of x I am getting from here, additionally I will also have to impose this periodicity condition. So that will give us an additional choice on the form which case should take. So this will give us the values of A, B, C and D, but this is not going to tell us what are the allowed energy values. How do we find what the allowed energy values are? That comes from this. Essentially only those K values. Now those K values will be equivalent to these things here, where when I move this function from x to x plus L, I will get a phase factor of e to the power ikl. So the periodicity condition will also be applied on top of this. So effectively what we will have is a system of more than 4 equations to determine the solution. So this system is kind of over specified. What does that mean? That means that these systems of 4 equations will not have a solution for all values of E. Only particular values of E will have a solution, will have a corresponding K value and will have a corresponding beta value. Otherwise, Ks and betas cannot be found for all energy values. So this is the notion that leads us to the formation of band structures. So aside from the 4 boundary conditions, which are these 4 equations, we will have a 5th condition, which is the periodicity condition, which is somewhat equivalent to the quantization condition that we introduced in the infinite potential well problem, where we said that okay, k can only be n pi by a, where a is the width of the potential well. Here similarly the width parameter again comes into play. Only those functions where psi of x plus L is equal to e to the power ikl times, oh sorry, I should have written it as ikx plus L, it's not ikl. Yeah, I knew I was making a small mistake here. So yes, so it is e to the power ikx plus L. So this can be further simplified as e to the power ikl times psi of x. Yes. So moving from x to x plus L will only introduce a phase factor of e to the power ikl. Only those values of k and the corresponding values of, because if I define k, I am defining e. If I define e, I am also defining beta. That is the understanding here. So only those k values are permitted. Not all k values will have, or rather, not all energy values will have a corresponding k value. We will see why that is the case. So that takes us to the second topic that we shall be looking at today, which is the band structure problem. So through this we will get these four equations. From here we will get another set of equations, combining all of them together and changing, like doing appropriate approximations. Here we will assume that, so this expression that we are getting here is under the condition where we assume that the depth, or rather the value of V naught tends to infinity, and the value of the width of the potential kind of tends to zero. So some approximations are done here to get this transcendental equation. So here this parameter xi is E by V naught. In the slides, the potential is represented by U naught, so it's written as E by U naught. But here I am represented by V naught, so it is E by V naught. It is the normalized energy quantity. So for the Kronig-Penney model, under certain approximations, we will get this relation, and alpha is essentially equivalent to the beta that we used here. So I've just taken this expression from the lecture slides. And of course, a plus b is L. All other parameters are the same. So what we have is this equation, which is a transcendental equation. Why is this a transcendental equation? Because the functions involved are transcendental functions. Like transcendental functions are functions that cannot be represented as finite length Taylor series expansions. Like you will need the infinite Taylor series. If you can even represent it as a series expansion, you will need the infinite Taylor series to represent them. They cannot be represented as polynomials or ratios of polynomials in x, or the function variable. So here now this is a function of the energy variable. So you can see that, because with alpha or beta in our case, we had the factor V naught minus E. So if I take the V naught out as common, I will have 1 minus E by V naught. E by V naught is what I'm calling xi. So essentially that is what we are getting here. Now this is the transcendental equation, and this equation will tell us how the band structures are emerging in this Kronig-Penney model. Now, of course, we have heard bands typically when we talk about conduction bands and valence bands. So the conduction band and valence bands of a material are represented by the occupancy of these energy bands. So with that, let's move on to the next slide. Yes. So now this is the transcendental function. So this is the left hand side, if I'm right. Yeah, so this is the left hand side. So this quantity here, this whole quantity here is what we are calling f of xi. Okay. And this is the plot of f of xi. As xi tends to 0, f diverges off to infinity, and it is an oscillating function, not a periodic function. And it can be seen that the the value of this function will eventually the value of the function will always vary between -1, not -1 to 1. It will keep varying between a positive and a negative value, and the time it takes to go from maxima to minima will increase after every successive oscillation. So this distance will be smaller than this distance, which will be smaller than the next time it comes and cuts 0. So the distance between 0 cuts will keep increasing. Okay, so that is this function over here. So this is the left hand side of the equation, LHS of the equation. And what we have is, on the right hand side, is a cos function. So this is cos k L, or cos k a plus b. Now what we know is this function can only take values from -1 to 1. So this can only lie in -1 to 1. Therefore, only the values of xi, that is E by V naught, which leads to this entire function being evaluated in the range -1 to 1, can I find a corresponding k value. So of course, right away what we can say is, for any given value of xi, there will be multiple valid k values, because the cost function is a periodic function. Also, for any given value of xi, even any given value of f of xi, there are multiple values of xi that are eligible. So what I mean is, going back to this graph, if I fix the value of f of z somewhere over here, then it is satisfied not by a unique xi value. In fact, it is satisfied by several, technically infinitely many xi values. So what is happening is, now the energy of this system is of course increasing, because this axis, the x-axis of this function, this is xi, so this is E by U naught, is E by V naught. This is of course increasing. Even as the energy increases, somehow the k values that we are assigning to these energies are still staying in a finite region. Essentially what that means is, and that is due to the fact that the cosine function is a periodic function. What does that mean? When we try to plot these regions, so what we are having is, first this shaded gray region, this gray bar that we have here, that is the first time. So this function takes the value +1, and this is where it takes the value -1. Above +1, no valid k values are there. Below -1, no valid k values are there. So this is the first set of allowed xi values for which a k value exists. So this is the first set of allowed energies, this is the second set of allowed energies, this is the third set of allowed energies, the fourth set of allowed energies. So now, using this information, what we will say is, now the cosine function, if we are moving from -1, if we are moving from -1 to 1, then cos, or rather let me say k plus b, k times a plus b will vary from minus n pi by minus n pi to n pi. N can be 1, 2, 3, so on and so forth. So essentially what is happening is, we now have a case where, okay, I shouldn't even say this. The more precise way of saying this is, it will be from minus n pi to minus of n minus 1 pi. So this is one region, and n minus 1 pi, not n minus pi, n minus 1 pi to n pi. So these are the allowed k values every time. Like this f of xi crosses the region -1 to 1 multiple times. Each time it happens, we will define a new set of k values. So initially n will be equal to 1. So it will go from minus pi to 0 and 0 to pi. So that first region is a continuous region. It's a contiguous region from minus pi by a plus b to plus pi a plus b. So that is what is given in this graph. Now the second case, we will move from minus 2 pi to minus pi, and then pi to 2 pi. So now the second region onwards, they are kind of spread apart. So we have this over here. So minus 2 pi to minus pi, and pi to 2 pi. So that will be corresponding to a different set of xi values. For any xi value in this region, like in this region, or this region, or this region, and similarly for this region, we know no valid k values are there. no valid Ks are present. So this condition is essentially what I mentioned over here. The periodicity condition will represent what K values, or rather what energy values are present in my system. Okay, so for only these values in the shaded region of energies will I have a bound state solution for this problem. So there is a region where I have allowed energies, then there is a gap, there is another region where we have allowed energies, and then there is a gap. So because of that, these quantities here, all of these are called the bands. They are the energy bands. And if we plot them as a function of the K values themselves, it will be some curves like this. The trend will more or less be parabolic. So that is why we have this parabolic case. I shall come to why this is so. I mean, this figure itself says it is the free particle case. So we shall talk about that. And what we can do further is kind of reduce this representation, because this is kind of unwieldy to look at, and we cannot precisely understand what is happening in this figure. So what we do here is we perform what is called the reduced zone representation. So these regions, this minus n pi to minus of n minus 1 pi and n minus 1 pi to n pi, these regions are the one-dimensional Brillouin zones. So this is named after the French physicist Leon Brillouin, so who was one of the earliest people to study solid structure from the quantum mechanical perspective. So these are the 1D Brillouin zones. So they are defined by these values, and in each Brillouin zone we will have an allowed set of energy values. So yes. So what we will essentially do here is the following. I will take this piece of the graph and I will slide it to this side. So now, so what is in the first Brillouin zone? So this region is zone 1. This is the first Brillouin zone. So I will take this part of the curve and I will kind of move it here. So these two values are bound to be equal. So instead of this, I will have a curve, or is it the other way around? No, I'm correct. Yeah. So this thing will go up over here like this, parallel to this, and I will take this part of the curve and I will represent it like this. So after the first energy band, we have the second energy band. Then again what we will do is, for the third zone, we will take this curve and keep it here, and this curve and keep it here. So for the third one, I will have a structure that looks like this. For the fourth zone, similarly, I will do what I did for the second zone. I will take this curve and translate it all the way back here. So this will come here and this will come here. So I will get this kind of a structure. So ultimately, in the reduced zone, so this is the reduced zone representation. Representation where we have the first band, the second band. What should be understood is, as we are moving from odd bands to even bands, we should know what the 0 corresponds to. So in this case, the 0 corresponds to k equal to 0. But when we go to band number 2, this corresponds to the point where k is, remember, this point is now over here and this point is at k equal to 0. So here k is plus or minus 2 pi. And above here, k is plus or minus another 2 pi will go. Because here, if you notice, this point is, oh no, over here also, like between any two of these regions, the values of k will match. So over here, the k value, like at the edges, the k values will match. Between the even and odd, at the minima and maxima, the k values will match. Between odd and even, the k values will match at the edges. So if I'm moving from odd to even, I'm supposed to look at the edges. If we are going from even to odd, from 2 to 3, then at this point, we should understand that the effective K, not the effective, the real actual K value is plus or minus 2 pi. Similarly, over here, these 2 points will correspond to plus or minus 3 pi. And over here, this will be plus or minus 4 pi. And above this, there will be another band. And there also the K equal to 0 point will stand for K equal to plus or minus 4 pi. So this is the reduced zone representation of the band structure. So I'm not doing any example problems here because most of them are covered in the assignment and I think they are straightforward. However, I will take one small example and I will come back to it after we talk about effective mass. So what we have is, let us say, okay, so first before going towards that, we'll have to define what are conduction bands and valence bands. So let me say a material has enough electrons to fill up all the available states in the first band, all the available states in the second band, and let us say it is filling up to this point. Let me use the black color here. It is filling up all the states up to here. So all of these are filled. From here to here, they are all filled. So in this case, which is the conduction band and which is the valence band? So by definition, the valence band is the highest occupied band. And the conduction band is the lowest occupied band. Oops. Lowest occupied band for the system. So this definition is essentially carried over from quantum chemistry. It's actually from what is called the molecular orbital theory. So this entire solid can be treated as a multi-atomic molecule, like of course, because these are all atoms that are bonded to each other. So in that sense, what we have, like in the case of like simple molecules, the atomic orbitals will combine to form what are called molecular orbitals. Here, a large number, a very large number of atomic orbitals will combine to form what are called the energy bands in a solid, and they also have similar behaviors or similar properties to the molecular orbitals. So the highest occupied energy level is the valence band, and the lowest not occupied. I should have said lowest unoccupied. Yeah, made a mistake there. This is lowest unoccupied band. So in this case, the highest occupied band is band number. Okay, so we are calling this zone 1, right? Fine, yeah. So this is the first band, second band, third band. So in this particular case, the valence band is 3 and the conduction band is 4. Now, just because I'm defining a conduction band and a valence band does not imply that we have we can decide if the material is going to be conducting or insulating. That cannot be said directly. To decide how that will, how conduction will take place, we need to understand the concept of effective mass. We shall be spending most of today's session in this part. The session has so far gone on for about an hour. So the next 45 minutes or something will be spent entirely on effective mass, because it is important to understand what this concept is, and the explanation will be done through a problem. It will be illustrative, and then we'll come back to the band picture here and discuss what is happening. Okay, so first things that need to be known about the effective mass is the notion of effective mass is used to describe particles in an interacting medium. It is not only fixed for an electron, it is true for all kinds of particles, even classical particles. So one common example that we can consider is, so for, again, like all of us are familiar with this notion of buoyancy. That is, if I have any object, if it is suspended in, like, the weight of the particle as measured in air will be lesser than the weight of the particle as measured in, say, water, and the difference in the weight is equal to the amount of the water that is displaced by the object. So that comes from the Archimedes principle. So this is something that we are familiar with since our high school days. So there, what essentially happens is, an object suspended in air will have a mass. Now, corresponding to that mass, if I tie it up to a spring balance, I will measure a weight. Whereas if the same object is immersed in water, the weight is reducing. So in this case, what I can treat it is, I can say it is effectively a particle of the reduced mass suspended in air. So whatever interactions we are having, we kind of average over the effect of the interactions and put all of that onto the mass term. So yeah, something just happened. Okay, nothing happened. Yeah, so yes. So that is what I'm mentioning. And in solids, the effective mass is the inverse of the curvature of the energy bands. So we shall come to this when we look at the example. So a free mass m. So essentially, when there is no potential energy, let us say the particle has mass m naught. Now, in some kind of a potential energy field can be equivalently described by a free particle with some effective mass m star. So whatever I'm having, a particle plus a potential, can now be combined to create a free particle of a mass m star. So that is all that we are trying to do when we are studying the concept of effective mass. And this is not an exact representation. This is not to mean that in all cases the particle will behave like a free particle of mass m star. No, up to a certain approximation. And the effective mass can of course be positive or negative. So again, going back to the buoyancy example. So okay, here let me just note down that effective mass is even relevant in describing buoyancy, the phenomenon of buoyancy. Oops, let me just make it correct. Yeah. Yes, this is a y. Why do I keep messing that particular y up? The second one seems to look more like a y. The first one always ends up looking like a g. Yes, buoyancy. Yes. So can we like visualize a system that has a negative effective mass? Yes, of course, like bubbles in water. Like bubbles have air, and of course the air is influenced by gravity. However, a bubble that is present in water will rise. It will move against the direction of gravity. So that particular bubble can effectively be described as a particle with negative mass that is present in like free space. If it has negative mass, then the gravitational pull will have the opposite sign, which means instead of being pulled, it will be pushed away. So a bubble that is rising with respect to the gravitational field can be effectively represented by a negative effective mass. So negative effective mass is essentially, and the same analogy holds even when we are talking about positive and negative effective masses in solids. I really hope, I mean, I didn't have this network issue today because I would have liked to have some people live in this session so that I'd have probably received some questions. However, in case people watch this video, Feel free to ask any questions you have in the course page. I shall address them in the next video. So negative effective mass is similar to bubbles in water. I'll elaborate on this in a moment. Okay, so that is what it means. Like the sign of the effective mass dictates the motion response to any external force that is applied. So if you have bubbles in water and if there is no gravity, like if I just introduce an air bubble in a liquid and suspend that in a water bottle and suspend that bottle in space where there is the gravitational forces are not that high, then that bubble will move freely like any other water molecule. Like it will not choose a direction. However, when I introduce it to a gravitational field, then what will happen is the bubble will rise with respect to the water. It will always try to bubble up, like that is what bubbles are. It will move to the highest point that is available in the bottom. Whereas all the water molecules will try to move to the lowest point that is available to them in the bottom. So the water molecules behave as particles with a positive effective mass, and the bubble inside it acts like a particle that is having a negative effective mass in the system. In reality, no negative mass particles are known. In fact, we can say with reasonable confidence that negative mass particles cannot exist. But depending on the kind of interacting medium it is present in, a system or a particle can have a negative effective mass. Okay, so and the negative mass only corresponds to the motion response. That is all. And even that will be replaced by a different concept as we are moving forward with solids. So we shall see that pretty soon. Okay, so now this is the example for the effective mass that we are looking at. So now this might seem like a very odd problem, and I've just given this, I've not mentioned anything else. The reason is, if I try to describe this problem here, there will be like 2 more slides of material. So rather than filling that in, what I thought is, I will just like explain it as we go. So what we are doing here is, now the energy, let me be more exact. So to understand the concept of effective mass, we need to understand what is called the dispersion relation. So what is the dispersion relation? That is the EK relation. Okay, so have we seen the dispersion relation before? Yes, we have. So this graph over here, where I'm plotting E with respect to K, is a dispersion relation. So any Brillouin zone representation is effectively a dispersion relation. This is the reduced dispersion relation. Okay, so the values of K and the corresponding E's. For any, in the reduced zone representation, for any given value of K, there will be multiple values of E that are defined. We have to understand it with respect to these appropriate signages. So this is like minus pi, both of these points correspond to minus pi, both of these points correspond to plus pi, or rather pi by a plus b, like the factors, please keep them in mind. And this is 3 pi, minus 3 pi, this is plus 3 pi, and so on and so forth. So this is how the reduced zone is constructed. So whenever you are given a symmetric curve like this for a 1D system, you can just move the appropriate segments of that curve to these regions so that they match. Okay, so yeah, coming back. So now this function, this is not the universal thing, this is in a particular band. Okay, this is in a particular band. So what I'm saying is E is given by M, where this quantity M is the free particle mass, free mass of the particle. So I'm not saying this is an electron, this is a particle in some environment, there is some potential. After solving the Schrodinger equation for that potential, this is the energy expression that I'm obtaining for a particular region of K. So for that, I will have to define what K naught is and what the allowed values of K are. Okay, delta K are. So let us say we are choosing a region where k naught is maybe, so let me say k naught is equal to, what shall we take it as? Should be a half integer. So I will say k naught is equal to, so let me say this is 3 pi by 2. K naught is equal to 3 pi by 2. And of course, delta k can be, as mentioned before, it can be from minus pi to plus pi. Okay, so delta k varies from minus pi to plus pi. Okay, so this is what is the appropriate parameters for this dispersion relation. So E as a function of k is given by this for a particular value of k. So if I'm stating this formally, what I will say is E of k, oh not sub k, what I will say is E of k is equal to h squared by 2m cos 8 k naught. Oh yeah, delta k should be out of the bracket here. So the bracket closes here. This part should not exist. I will make the appropriate corrections as in the final version of the slide. Okay, cos 8 k naught plus delta k, where I'm saying that delta k belongs to minus pi to pi, and k naught is equal to 3 pi by 2. Okay, so now this is the dispersion relation. What we are, so what we shall do in this is we shall first find the value of E at the edges. Okay, so E of k at the edges of this region defined. So that is the first part. And then what we shall do is we shall find out dE by dk and d squared E by dk squared. Okay, we shall find these two quantities and then we shall look at the effective mass values. So these are the three things that we shall do in this exercise. So starting a new slide. Okay, so the first part, like E values at delta k equal to minus pi and delta k equal to plus pi. Okay, so what is happening here? What we can say is, so we know k naught is 3 pi by 2. So let us just write what the function is. So E of k is equal to h bar squared upon 2m. Oh, okay. Did I miss something? Yes, I did miss something. Yeah. So 3 pi by 2 is not a good case. So let me say, yeah, I made a small mistake. So in this case, what I'm going to do is I'm going to choose a better value of k because I just realized what I have done. The whole thing should be a half integer. So let me say k is equal to pi by 16. Okay, yeah. K naught is pi by 16. So now the whole problem will become very simple and you'll see what is happening here. No. Yeah. Okay, so, and K naught is pi by 16. Yeah. Yeah, sure. So now what is happening here is, sorry, the function that we have is cos. Now since K naught is pi by 16, this will become cos pi by 2 plus delta K. That's all. Because 8 times 16 is 1 by 2. So we'll have pi by 2 plus delta K. Now this is nothing but cos pi by 2 plus theta is actually h squared by 2m sine delta K, where delta K belongs to minus pi to pi. Only for these values. So what is happening in this case? So if I draw E versus K, what is happening is at delta K equal to 0, of course E is 0, and it will go up, come down. This is delta K is equal to pi. Similarly, this will go down, come up. Delta K is equal to minus pi. So this is the E-K relation. Now this problem has no physical relevance. This is just an example. So now we know this is the sketch and the value at plus k and delta k is equal to plus pi and minus pi are again 0. So this function varies from, like, it has a minimum energy of minus E and a maximum energy of plus E, and in the domain that I've defined, it has at the edges it has 0 values. Okay, so now that is the first part that is done. So the second part is, let me use a new slide for this. So this is the dispersion relation. Oh no, here I shouldn't say K, it should be delta K. No, let me do one more thing and make it clear. Now all of this is defined with respect to some K naught. So what will actually happen is, in the K region, so this is E versus delta K, whereas in E versus K space, this will be centered at pi by 16. It will be over here. Okay, so this point is pi by 16. And from here, we will move pi this direction and pi this direction, so it will no longer be symmetric here. So this, let me draw it slightly bigger. I drew big axis but small points. So if I kind of like zoom in, as I had done for this case, the 0 will be at delta k equal to 0, but the value of k itself is not 0. So it will be slightly translated to this side. And from here, we will have this and this. This is k naught. Okay, and please assume that this, like, the curved regions that I'm representing are like symmetric. Again, as mentioned before, drawing is not one of my strong points by far. So this is E and this is Q. Yes, this is how it will be. So it will be shifted by this value K naught. Okay, so this is the value of, this is my EK relationship. So this is E versus delta K, translating it So this is my dispersion relation that has been sketched. Now, what is the first thing we know? We knew the notion of effective mass. In solids, the effective mass is the inverse of the curvature of the energy bands. So in this case, in this like toy example, which has like next to no meaning, the curvature of this line, this EK line, is going to give somehow, it's going to give us the effective mass. What does that mean? So to do that, we will have to evaluate the derivatives. Okay, so first we need to find dE by dk. Now, yeah, dE by dk. So that is just one second. Oh, why am I doing that? So d by dk is d by dk of this function, which is h squared by 2m into cos 8 k naught plus delta k. Okay, so now d by dk, like essentially k naught, these are all constants defined in terms of k. So what we are supposed to do is we are supposed to treat this as k plus delta k. Okay, so when taking the derivative of this function, what we will do is we will get 8, or rather minus 8 h squared upon 2m sine 8 k naught plus delta k. Okay, now why is this factor of 8 important? Because if I shift k naught by k plus pi by 4, this function will achieve periodicity. Okay, so that part should be understood. Yeah. Yes. And similarly, d square e by dk squared is again a factor of 8 will jump out, so we will have 8 into 8, that is 64. I could have chosen 4. I don't know why I chose 8, and doesn't matter. So 64 h squared by 2m. Again, we'll get back our cos function. Cos of 8k naught plus delta k. Now, in general, the curvature of a function, so the curvature kappa for any function of the form y equal to f of x, the curvature is given by this quantity. It is given by f double dash of x divided by 1 plus f dash of x the whole squared whole raised to the power 3 by 2. So this is the expression for the effective mass. Sorry, this is the definition for the curvature. However, we shall not be using this expression. Like you would have noticed that in class, this is not the expression that is considered. The expression that is considered is okay. So we'll 1 over k is therefore the expression for curvature is not used in the lectures, which is why I'm kind of doing this derivation. So f dash of x whole squared 3 by 2 divided by f double dash of x. So in the denominator, we have the second derivative of this function. So this quantity d square e by dk squared will appear in the denominator. So now this is what I'm calling the effective mass. This is what I'm calling the effective mass. Now what we can add to this is, now remember what these band edges correspond to. These are the lowest energy level and the highest energy level in this region. So by that rationale, what I'm going to do is I'm going to now focus only in this region and this region, like around the maxima of this function and around the minima of this function. Okay, so yes. Okay, so that is the part where I shall be concerned with. Or should I do this? You know what? Yeah, one more small rectification. Or no, let it stay like this. Not a big deal. Okay, so we are considering the maxima point and the minima point. Okay, and I should have introduced uh, this. Yes, it should have been 8 times k plus delta k, because then it will make sense. So let me retroactively go and make some modifications here. Let me say this is minus pi by 8 to pi by 8. Yes, now all is well. Yeah, I was constantly having that trouble, and now it's no longer a, where is my, yes, now that is no longer a problem. Yeah, so if delta k varies from this to this, so that being the case, this parenthesis is correct. Yeah, now I don't have to do any major changes. Okay, and here it is understood that these things are in the appropriate, and my variable k is now k naught plus delta k. Okay, yes. So now where will the maxima of this function occur at? In this case, so here, so this is pi by 8 minus pi by 8, and here the whole thing will be shifted by pi by 16. So this will be pi by 8 plus pi by 16. So that is should be what, 3 pi by 16? Yes. And this will be shifted this way by pi by 16. So that's minus. So this will be minus pi by 16. Yes. So yeah, as you can see, I'm not very good at drawing. Technically speaking, my origin should have been over here. Can I rectify it? Of course I can rectify it. Yes. So yeah, now this is how it will be. So since I've shifted this whole scene by, yes, so this is 0, k naught, which is pi by 16, and yes, so this is the dispersion relation that we are looking at. Yep, all is correct now. And yes, so coming back, so these are our derivatives. Now at the maxima and minima, I know f dash of x is 0. At extrema, like collectively those points are called the extrema. At extrema, f dash of x is 0, which implies at the maxima and minima points, I can say this is valid, f double dash of k. Which is why when we represent the effective mass of the system, we say it is h bar squared into 1 over d square e by dk squared. This is the expression that you would have seen. So this is at band edges. So if this were to represent a solid state band, then this and this point would be my edges. Okay, so Now I'm not going to go through the calculus to do the calculus to find the minima, because I've already represented the graph here. So from here we can tell where the minima and maxima will occur. So this will be in the middle of these 2 points. So this is pi by 16 to 3 pi by 16. So this is going to occur at pi by 8. And here this is of course occurring at 0. Okay. So, oh no. What have I done? This is pi by 16 plus pi by 16. Yes. I'm sorry. Apologies. False alarm. Yes. So this will be pi by 8. This will be 0. And will it be though? Yes, of course it will be. Yeah. So, yes. So at first, let us look at the maxima point, k equal to pi by 8. I am telling that the effective mass m star is h bar squared into 1 over d squared e upon dk squared. Now you're going to see what's going to happen, h bar squared. Now what is d square e? That is this quantity. Now at k equal to pi by 8, which corresponds to delta k equal to like pi by 16, this whole quantity k naught plus delta k will come out to be pi by so in this graph, yes, so all of this will come out to be pi by 8. So yes, what should it be? Yes, yeah. So at this value, at this point, like essentially what is happening is my second derivative is just a constant times the function. So the value of the function, like essentially at this point, if cos kx is achieving the maxima, then the second derivative also will correspond to the maxima point. So this function will evaluate to 1. Okay, so the trigonometric part of the function will evaluate to 1. So what I'm left with is h squared by h squared into 1 over h squared upon 2m into 64. So the h squared and h squared will cancel out. 2m will show up at the top, and we will have m over 32 as m star. So this is what is happening here. Now at this energy value, at this particular k value, at this point in my dispersion relation, I can treat my particle as a free particle with effective mass 1 by 32. So this is the effective mass. Okay, so that is what is implied by this whole exercise. Now similarly, what happens at k equal to 0? At k equal to 0, what will happen is, or rather at delta k equal to 0, not k equal to 0, delta k equal to 0. So this is delta k equal to plus pi by 8, or rather plus pi by 16, not plus pi by 8, which will correspond to an actual value of pi by 8. Yes, because this entire distance is pi by 8. This distance is of length pi by 8. Yeah, I'm sorry, my choice of variables has led to a lot of confusion. This length between these 2 points is pi by 8. This is from 0 to here. This is the actual point pi by 8. This is from pi by 16 to 3 pi by 16. So the distance between them is of course pi by 8. Here we go from pi by 16 to minus pi by 16. So again the distance is 2 times pi by 16, which is pi by 8. The middle of that is occurring at the origin. Okay, this is k naught. Yeah, now everything is clear. So the minima point occurs at delta K equal to 0. So over there, what I will be left with is, again, the whole thing follows with only one change. The change is this. Instead of +1, we will have -1. Okay, oh, sorry. Previously, we would have had -1 because there was a -64 here. And in this case, we will have +1. Yes, so this is minus into this. So this is minus n/32. And at the minima point, same expression, 1 over d squared E upon dk squared. So this will correspond to h squared, into 1 over h squared by 2m into 64. So now this will lead to a positive value, m/32. So now what does this mean? So this is the effective mass. Due to the choice of our dispersion relation, the effective mass is the same value, same magnitude at both the minima and maxima points, but the sign is changing. At the maxima, so this we can say as a general rule, at band maxima, m star will be negative. At band minima, m star will be positive. Now, what does this mean? So let me consider the effective Brillouin zone representation of the Kronig-Penney model. So we have the first Brillouin zone over here, and then we'll have the second Brillouin zone over here, and we shall have the third Brillouin zone occurring over here. Again, the curves are kind of skewed, please don't mind that. Now, what I'm doing is I'm considering zone 2 and zone 3. The reason I'm choosing that is the minima and maxima occur at the same K value and it is easy for us to look at. So what I'm saying is at the band maxima over here, I'm saying the effective mass of the electron is negative. Over here, I'm saying the negative mass is positive. What does that mean? Again, going back to what I wrote in a few slides before, the sign of the effective mass dictates the motion response. Now, what does that mean? What does motion response mean? It means this. Now, let us say I have one electron over here. Let me use my black over here. One electron over here. Okay, at the band minima over here. Now, as I'm applying a force, what am I doing? I'm increasing the energy of the particle, like it is gaining energy because of the externally applied force. Now, this force is typically an externally applied voltage. So, some energy is gained. Now, when that energy is gained, what will happen? It will go to one of the higher energy states because this is the energy axis. This is the energy axis. Okay. So what are the higher energy states? It can be some point over here, some point over here in either direction. So this is minus pi by L. Yeah. Pi by L plus pi by L. Okay. So it can go to values like this, like depending on how much energy is supplied, it will either pick a value to the left of this point, to the right of this point. Now the catch is this. As it is going to this point, what is happening? The energy is rising. So, and one more thing that we have to remember from our original discussion is this quantity h bar k. This was covered in my first session also, and it has been covered in the lectures also. This is the momentum. Okay. So this is the momentum of the uh, electron or the particle in quantum mechanics. So when I'm applying a voltage to a particle that is present here, it will move to one of the empty states which corresponds to a higher, like this is not exactly the momentum in this case, but this represents the momentum. So giving E leads to increase in momentum, like the magnitude of momentum. Increase in the momentum. Now imagine the same situation for the band number 2. Now, I can't assume an electron is existing at the top energy level itself because that will never happen. Energy levels always fill from the lowest energy to the highest energy because generally all physical systems try to stay in the minimum energy configuration. So, what we have to visualize now is, let me assume, which is why I did like a very thick black circle over here. Let me say that there is a vacancy at the top of this band. Let me say that this point over here is empty. It is free for an electron to be occupied. Now again, when I supply energy to this system, an electron from either here or here will jump into this vacancy. Because I've supplied energy, it has enough energy to move from this point to that point in the dispersion relation, from this k value to the other k value. So what is happening is the electron has gained energy, but what happens to the vacancy? The vacancy will now shift in some direction. Now the point is, the vacancy will always shift in that direction that is opposite to the electron, because if an electron with a, oh no, why did I do that? God, yeah, I just realized what I did here. I flipped the x-axis. Yeah, so this is, yeah. So when the electron jumps from here to here, the vacancy has moved to, like if it's from the negative to the zero region, it is coming from here. Yeah, so at k equal to 0, it does not imply that the momentum is 0. It does not imply that the electron is static. This is just an approximate representation. I should rather say the sign of k gives us the sign of the momentum. Positive, yeah, that would be a better. Oh no, even then, like k equal to 0 will correspond to. So, except at k equal to 0, if k is positive, it means the electron is moving along the positive direction. If k is negative, it means the electron is moving along the negative direction. Just think of it that way. Okay. Yeah, coming back. So, if an electron with a negative k value comes to this zone, now the hole has actually moved in the opposite sense. This means now this, yeah, I use the word hole, this vacancy now has a momentum. Like previously, I can say that it corresponded to the k equal to 0 state, but now it will correspond to a non-zero k state and it will start moving. Like if a positive, like if something with a negative k value comes here, then this hole will go here. If something with a positive k value comes here, then this will come here, which implies the electron, to gain more energy, the absolute value of the momentum will have to always reduce. The magnitude will increase, but the signage will always reduce, because what will happen? A vacancy will be created here, which means one electron here will move here, another electron will move here, another electron will move here, which implies the total momentum value will become less and less positive. In this case, what will happen? The electrons will keep shuffling forward, which implies, again, the value will become less and less negative, which implies if there was a vacancy here, supplying energy to the system somehow is reducing the momentum. Means the electrons are moving less and less in order to reach the high energy state. So that is essentially what is implied by the negative effective mass. Negative effective mass is not some anomalous quantity. It just says what happens to the momentum as energy is supplied to the system depending on its environment. In this case, these are the available energy levels, so the electrons cannot do anything else unless and until they jump from here to here. As long as they are confined to this band, that is all that they can do. And this negative effective mass is further simplified by just treating, like, because since I mentioned that the force that is applied in electronic systems is represented by some electric field E. Yeah, again, okay. So let me call this the field. This is not the energy. Please do not confuse it. So the force vector is Q times E. Now, what is seen is that when I'm applying a force, the momentum is changing in the opposite sense when I'm in band number 2, when I'm near the top of band number 2. So what we can do is, instead of putting a negative sign on the mass, what we can say is this is a positively charged particle with positive mass. Because negative mass is a very uncomfortable quantity to deal with, what we will simply say is this is a positively charged quantity, and that positively charged quantity is what we call a hole. So that is a hole. So essentially, the negative effective mass that occurs at the maxima is absorbed into the charge of the electron itself, and then we treat it as a positively charged particle with positive effective mass. So this is the idea of effective mass. One final thing, let us look at the effective mass at, say, delta K equal to, so what happens to m star at delta K equal to pi by 16? What happens at this case? Sorry, not delta K equal to pi by 16, and delta K equal to 0. Sorry. So in this case, what happens is, again, going back to our second derivative expression, if delta K is 0, then what I'm left with is 8 times K naught, which is 8 times pi by 16, which is 0, which implies this quantity here at delta K equal to 0 for our particular thing will be, technically speaking, this will be minus infinity. In general, when I'm considering the band from the minima to maxima, what happens is, over here, dE by dk, or rather, let me say d square E by dk square. Why did I do dE by dE? Yeah. What I mean is, d square E by dk squared is negative over here because this is the maxima point. Over here, d squared E by dk squared, that's like from the definition, that's from calculus. This is positive over here, which implies somewhere in between, if this is a continuous function, d square E by dk square will become 0, and that point is actually this point. That is where k equal to k naught, which is why I'm considering the case delta k equal to 0. So in that case, okay, it won't be minus infinity, it will be just infinity. Yes. So in that case, what will happen is this reciprocal factor, again, I don't have to care about what the value of f dash is. Since this is becoming infinitely large, m star will become infinite. So what does this mean? What this means is, in this region corresponding to this k value, so those k values will be somewhere over here and here. Okay, they will be in this region, somewhere in the middle. Oh, I mean, generally. Now, in that region, since the mass is infinite, what happens is, I mean, again, what was our conceit? Our conceit is that a particle of free mass m naught in a potential energy can be treated as a free particle with effective mass m star. Now, m star has become infinite. This implies no external force, or rather, not no external force, I should say. I mean, if a particle is of infinite mass, no matter how much force I apply to it, it won't move. It's an immovable object, essentially. So, external force causes no motion. external force causes no motion. So that is what it means when we have effective mass infinite. Plus infinity, minus infinity, doesn't matter. If the effective mass is infinite, it means no amount of electric field that I apply to my system within a limit. Again, all of this is within a limit. I can apply an electric field that is so large that the material structure itself changes. In that case, none of these things hold. That is why I said up to an approximation. So for acceptable values, no matter how high I go, particles in this region will not shift from one k value to another. That is why in general we say, now this is important, this is the takeaway from this entire discussion: conduction takes place at the extrema of bands. That is it. It will either take place at the minima of a given band or at the maxima of the given band. Those are the only two regions where conduction can take place. Why? Because those are the regions where I will have acceptable finite values of effective mass. As and when I'm moving away from the extrema points, the effective mass will become larger and larger and larger, and at the inflection point where the second derivative goes to 0, the effective mass becomes infinite, and because of that, they will not participate in conduction. That is the takeaway here. So, going back to this example, now I'm saying that the electrons are filled up to this point. So, in order to find out if that material is conducting or insulating, what we are supposed to do is, we are supposed to find out what value of K it corresponds to. We will have to see where, like this is band number 3. So that this is band 1, band 2, band 3. So this is somewhere over here or on the opposite side. Over here, we'll have to see what the effective mass is. If the effective mass is finite, then yes, some amount of electric field applied will cause some change in the values of K, which means the electron momentum is changing. I can move my electrons according to the external force that is applied, and therefore this system is capable of showing some conduction. Generally, the closer it is to the maxima or minima, the better the conductivity is. If a band is filled only up to the midpoint or half filled, in general, we will understand that this corresponds to the place where the d square E by dk square is 0, which implies these are electrons with infinite effective mass. So no amount of energy that I supply is going to cause any conduction within the band. Like I cannot make it move within the band. The only option I have at that case is to lift an electron from here and place it here. Essentially give some energy to kick it from here to here. So that is essentially what is called as excitation. So this case where the electron band is like half filled or completely filled, where there are no available K values, these are what happens when we consider materials like silicon at 0 Kelvin, or say, well, nitrogen is a bad example. What can we take? Yeah, arsenic. So arsenic is, although, okay, no, I will not take arsenic because arsenic is different. So essentially, if a band is half filled, yeah, there are no famous examples for this, unfortunately. But if a material is such that it is only filled up to this point, then in general, they will act as poorer conductors. If the electrons are filled all the way up to the top of the band, then conduction will be better. So more electrons present at band minima or band maxima implies, or rather more gaps present at band maxima or more electrons present in the band minima will lead to a high system with high conductivity, a material with high conductivity. Okay. And anywhere where the band is only partially filled, we will say that yes, of course, it will act as an insulator. There is one small catch here, that is this gap. As you can see, this gap becomes smaller and smaller and smaller and smaller as we go higher and higher and higher, which implies even in a half-filled band, provided enough of these bands are filled, I can come to a point where even a small energy excitation will lift my electron from this band and move it to the next band. because the band gap is very small. As I move successively above, this band gap will become smaller and smaller and smaller. So the band gap here is this much, here it is smaller, here it is smaller still, above it will be even smaller. And that is generally true in realistic 3D materials also. As we move to higher and higher energies, the band gaps will become smaller and smaller and smaller, which is why systems are, atoms with lots of electrons, when they form solids, they invariably behave metallic. This is the reason why in the transition metal and inner transition metal region, we find a lot of metallic elements. Even p block elements will start showing metallic behavior if they can form a solid. The example for that is actually arsenic and antimony and these elements. These belong to the nitrogen group. So when there are few electrons, that material doesn't even form a solid. But when there are enough electrons, not only can they form a stable solid, that solid is capable of showing conductive properties also. So depending on how much bands are being filled, we can decide if the material will be a good conductor or not. This is something that is actually taken into consideration when people construct devices. This is also, one of the reasons why we like when we consider intermetallics or compounds for creating other like alloys, essentially like gallium arsenide or any form of doped compounds. Essentially, we will choose electron-rich materials or electron-deficient materials to introduce the appropriate kind of charge carriers into the system. The motivation effectively comes from here. We will introduce a system that is either rich in electron or deficient in electrons that will create the appropriate vacancies in the bands, or rather in somewhere in my system. So they need not even be a part of the bands. They will introduce what are called quasi-Fermi levels, and that will contribute to charge carriers like either electrons or holes. Another important thing is, the reason why I spent so much time here is this quantity here. So the effective mass, it is related to the curvature. So later on, when we talk about strain engineering, where we will modify the lattice parameters based on the desired performance of our device, we shall be modifying the lattice parameters by introducing lattice strains. So what that will do is that will effectively change the band structures in different directions. When that happens, depending on the curvature, the electrons in different bands, different directional components of the bands will either behave as heavy electrons or light electrons. We need not go into that right now. That will become the central topic of discussion a few weeks down the line. But all of that comes from this notion, comes from effective mass is the inverse of the curvature. It comes from here. So all we have to do is look at the curvature. Greater the curvature, take the inverse of that, lesser the effective mass. Points of inflection where there is no curvature, where the band becomes flat, we will have infinite effective mass. So that is the takeaway. Since I have run out of time, I will not cover density of states in this session. There are only a couple of questions in the assignment, and if you follow the slides, you should be able to answer those questions. Density of states will also feature in week 3 of our course. So next week's session, I shall cover density of states. Before that, there was a question from in the forums. Like as I mentioned before, I will be covering any questions that are being asked in the any questions that have been asked in the forums. I shall also be answering them here. So this question was essentially from the earlier lectures, where we have a source, a channel, and a drain. And so the instructor, Professor Vishwendra, mentions that the source, so this is mu source, this is mu drain, and this is the channel. So Professor Vishwendra says that yes, so the source will introduce electrons from this energy level to this energy level, and drain will try to take electrons from this energy level to this energy level. So what does that mean? Does the source only fill electrons from the middle? So the question was essentially this: does the source only fill up electrons from the middle of the band to the top of its Fermi level? The answer to that is not so simple. It's not a yes or no question. What we should understand here is that this is not the initial configuration of our system. This is not the initial configuration of our system. What essentially happens is, originally, like and in equilibrium, like all systems start from equilibrium. So one is supposed to look at the equilibrium band structure of the material. So the equilibrium band structure will be this. I will have a source, a channel, and the drain. Like whatever happens, whatever necessary band, I shouldn't say bending, like band realignment needs to take place, will take place, and all the Fermi levels will be aligned. So at equilibrium, mu s is equal to mu d, and typically, majority of the states at zero temperature, all states below this will be filled. That is how it will be. Like the Fermi level will be uniform across the material, source, drain, and channel. So source, channel, and drain, if I'm going from left to right. Okay. So what I will do is I will select this whole thing, and I will just drag this down here, and I will call this answers to queries, so that it is clear what this part of the discussion corresponds to. Answers to queries from the forum. Okay. So this is how the system will be. Now, when a potential is applied, so here it is obviously understood that this gap is plus QV and this is minus QV. Like essentially this gap that is introduced between these two Fermi levels is the externally applied voltage. So this, like when I apply a voltage, I come from here to here. After this happens, electrons with energy here up to the Fermi level of the source will have free states on the drain side, so they will tend to move. And of course, as the electrons move from here to here, any electron that are present on the source side will have vacancies over here, so they will try to populate those vacancies. So in that situation and that situation alone, the source will fill electrons with energies starting from this middle value all the way to mu s, from mu t all the way to mu s. In general, it is not the case. In general, one shouldn't say that the source will only fill from the drain level to the top. That is not the case. In general, in equilibrium, not in general, in equilibrium, the system will have a uniform Fermi level. So mu will be the same across the material. So no currents will flow. There will be a net charge transfer equilibrium. This is a non-equilibrium situation. So yes, electrons will move from here to here and here to here. This is strictly a non-equilibrium situation. Then and only then is that statement correct. In equilibrium, rate of electrons moving from here to here will be the same as moving from left to right, will be the same as moving from right to left on average. Because in equilibrium, no current flows through a material. Okay, so that should be understood. Unfortunately, I did not get the name of the learner who asked this question, so I'm unable to address them directly. However, I shall notify on the forum that this particular answer to this question is available in the last part of the video. So with that, I come to the end of today's discussion. Once again, I apologize for the technical difficulties. Hopefully by next week, these issues will be fixed and the session will start on time and proceed without any interruptions. I mean, a few people joined on and off, but nobody has stayed through the session. So hopefully next time things will go well, and people will be kind enough to stay through the entire session, because as I mentioned before, talking alone to a display for 2 hours is kind of weird and exhausting. So with that kind of remark, I bring today's session to an end. We shall meet again same time next week. Thank you.